Bob here from racecarbook.com, airdensityonline.com. We're going to set up a Pro-Calc jetting calculator for a 305 circle track engine. First thing we're going to do is go to our new baselines profile and see if there's anything on here that looks like a circle track engine. Well, before I select that, let's go over here to Info. Sample baselines, normally naturally aspirated. 305 horsepower peak. Okay, that is normally aspirated, engine size 305, that's what we want. Running methanol at horsepower peak with a high speed. I don't want to do that. It gets too complicated starting out with a high speed. So let's go to this next one. Normally aspirated 305 torque peak. That is a normally aspirated engine size. Running methanol at torque peak without a high speed. Okay, that's what we want. So let's go back to our sample baselines, and we'll go ahead and select that profile. Okay, going down the list, this will be our naturally aspirated 305, and this is our torque peak. This will be a setup without the high speed. Okay, this is a 305 cubic inch, so that's correct. We're going to select 100% volumetric efficiency. This engine may be a little bit more than that. For the purposes of this, we're going to stick with that. Fuel pump, we've got to determine what fuel pump we have. We go to our fuel pump size list. We have a Waterman, and it's a 250400 twin gear, and it's a used pump. So I'm going to select 361 for the pump size. Okay, that's also an 8,000 RPM rating, or 4,000 pump RPM. It's an 8-cylinder engine, 1 nozzle per cylinder. I have no idea what my main is, however my sample profile suggested a 70, so we're going to leave that alone. I don't have a high speed in it, and I don't have a second high speed or pump saver or pump loop. Estimated pressure, we don't know what that is either. Just a footnote, these high speeds, or the second high speed, is not a place to put the secondary bypass. That's an off-idle pressure only and does not show up in this list at this time. Coming back down, I'm going to leave my target RPM at 5,000 RPM because this would be a medium range or medium course where I'm coming out of the turns at 5,000 RPM. Okay, again, there's no nitro in this combination, so I'm coming down to my weather data. 80 degrees is typically where we're at. 40% humidity would be typical of the humidity in the area. This is a track that's in slight elevation, so the uncorrected barometer would be 28.5 would be a typical value. Typically Midwest track locations, foothills. Looking at my nozzle size, again, this was suggested for a 305 in this combination, so we're going to leave that alone too. I'm going to go ahead and create baseline profile. Okay, this one ends up an optimum air-to-fuel ratio of about 4.6 to 1. That's a pretty good air-to-fuel ratio for the bottom end coming out of this engine. A lot of people run them a lot richer than that. Some people run them a little leaner than that, but 4.6 is a very good value, so we're going to leave that alone. What we're going to do now is set up the high speed. To do that, I go to optional, and I'm going to copy this. Okay, now the volumetric efficiency for this, I'm going to put at about 80%. Again, some engines are higher. The fuel pump will stay the same. The RPMs will stay the same. The number of cylinders, nozzles per cylinder, and our main bypass will stay the same. Now, we don't know what the high speed is going to be, so we're going to leave that blank. Coming back to the volumetric efficiency, I want to point out something. A lot of dyno setups produce volumetric efficiencies. It's important that if you're going to use a dyno setup, double check to see if the instrumentation that was used to determine that was calibrated and that it's a good number. Okay, coming back down, everything else should be the same, including the target RPM, our weather, and then our nozzle size. Okay, now create baseline profile. Okay, so what this indicates is if we don't have a high speed, the air-to-fuel ratio gets real rich real fast. That's very rich, and there's probably going to be a 10, 15, 20 horsepower loss from because you're not using a high speed. So we're going to go up here to the air-to-fuel ratio calculator. We're going to select the HP, the horsepower profile. We first of all have to enter the weather from our baseline. This is 80 degrees, 40% humidity, and 28.5 is the barometer. Just a reminder, ProCalc does not pull the weather out of the baseline. That always has to be re-entered for whatever evaluation that you're doing with the jetting calculators. Okay, go ahead and get air-to-fuel ratio. And there's our 368 air-to-fuel ratio, which is too fat. So what we want to do now is look into adding a high speed for our 80% volumetric efficiency. So again, one of our jetting books suggests starting out with something similar in size to the nozzle. So put in, say, a 25 in there. Okay, 395. It's starting to lean out on the high end, but that's not lean enough. So let's go ahead and increase the size of our high speed. Let's go to 35. 420. Okay, that's starting to get a little bit less rich, but it's still on the rich side for the high end. Let's go back to the high speed and let's put another one in there. Let's put a 45 in there. In a new combination, this would be a reasonable progression as you're going up. Go ahead and get air-to-fuel ratio. Okay, we're at 453. That's still on the fat side, so we're going to go back here and we're going to go bigger in the high speed. Let's go to 55. Get air-to-fuel ratio. 495. Okay, we're going to start at a point now where we're probably where a lot of people run, but I'd like to lean this out a little bit more. I want to really make some suds on that high end, so I'm going to come down here and I'm going to go a little bit leaner. Let's go to 60. Okay, we're at 520. That's a pretty good high-end air-to-fuel ratio for a circle track car. And that would be a reasonable value to achieve. Going back in here, how big of a high speed does it take to get that? 60 thousandths. Okay, I'm going to go back to my baseline profiles, and I'm going to put that 60 into the baseline. And now I have it. I have my low end set up without a high speed at a 4.6 coming out of the turns. That's a lot of fuel in there for response. And then as soon as the high speed opens, it leans out as the RPMs climb to a 520. Before we continue, I want to demonstrate something else. I'm going to go back to the torque peak baseline, and I'm going to illustrate something with one of the calculators. Go to air-fuel ratio calculator. Get air-to-fuel ratio. You have to select the torque peak. Okay, get air-to-fuel ratio. Okay, this is showing me the estimated pressure at 5,000 RPM of 80 psi. This would be the setting, the poppet setting for your high-speed bypass, so that it would open at 5,000 RPM with this nozzle combination and main bypass combination. So right now what we have is our 22 thousandths nozzles, an 070 for the main bypass, in the other profile a 60 thousandths for the high speed, and a 80 psi opening pressure for the high speed bypass. I'm going to do one other thing. Keep in mind that 80 psi. Okay, we're going to show you one more thing to do with this. Go to the baseline profiles, edit this baseline. Okay, go down. 305 circle track engines routinely do not go to 8,000 RPM. Typically, especially with flat tappet cams and stock cylinder heads, maybe the low 7,000 RPM range is more typical. So what I'm going to do is demonstrate some pressure analysis for this to examine the flat line. I'm going to go to the air-to-fuel ratio calculator. I'm going to switch over to my horsepower peak combination. Get air-to-fuel ratio. This is showing my pressure. And that would be with the high speed. Remember, we determined without a high speed that it opened at 80 psi. Okay. Now, I'm going to go down here to my target RPM, and I'm going to put in 7,200 for my target RPM. Get air-to-fuel ratio. And what this shows me is that at 7,200 RPM with the high speed open, I go to 84 psi. Okay. That means that I'm flatlining. It goes to 80 psi, opens, and it flattens out to up to 7,200 and climbs a little bit to 84 psi. That is typical of a normally aspirated fuel system with a high-speed bypass. Thank you for your time.